Hello, everybody. So in the previous video, we defined what Turing machines are, and we discussed mostly what is deciding and what is recognizing. And in this video, we're going to ask what would have happened if we defined Turing machines a little bit differently. Would we get something completely different, or will we get the same thing? And this would lead us to the Church-Turing thesis. We will also discuss non-determinism in this context. So these are Church and Turing. So we define Turing machines as this finite state control that has a read-write head to an infinite rewritable tape, and we define the input to be written on the left and the tape to point to the left. We also define that if you move to the left from the leftmost position, then you're staying put. And all of these seem pretty arbitrary. So what would have happened if we, for example, decided that if you're in the leftmost position, you do something else, or that perhaps there is no leftmost position. Perhaps you can go infinitely to the left as well. And we actually mentioned that the original idea was to kind of formalize or abstract what humans do when they have access to a piece of paper, and so this piece of paper could be two-dimensional. And we kind of mentioned that that wouldn't have changed a lot. So let's give another variant. And this variant will be actually very useful for us, and show a bit in more detail how this variant actually gives you the same thing, gives you something that's equivalent to a Turing machine. And this variant will not have a two-dimension tape, but instead what it will have is some constant number of states. So you still have finite states control, but now you have three read-write heads pointing to three rewritable tapes. And again, it's pointing at the leftmost position. And let's say that the input is written in the first tape, in the topmost tape. And we have your K. K is three tapes, but it can be any other constant number of tapes. So does this give you something stronger or not? A priori, without thinking much, we could say, oh, perhaps it is a bit stronger. In fact, when we'll talk about efficiency, we will see that in some sense it is stronger. But when we talk about computability, it will turn out to be equivalent. So to formalize that, the main difference is that we need now a transition function that has your current state, but as the K symbols that you are reading instead of instead of one symbol that you're reading, and you need to specify K symbols that you are writing. And also for each one of the tapes, are you going to the left or to the right? So that would be a way to formalize a multiple tape Turing machine. And the theorem is that every multi-tape Turing machine can be transformed into a single tape Turing machine. In a sense, it can be simulated by a single tape Turing machine. This will mean that whatever can be computed by one can be computed by the other, and these are equivalent models of computation in terms of what's computable, what's recognizable. So the way we will do that is by having the single tape simulate the three tapes. Now there is a problem. How do you capture three infinite tapes in one infinite tapes? There are various ways of understanding that. But one way is just to say that we don't care about all the tapes. I mean, the entire tape. We only care about the position of the tape that have something in it. So what we can have in the single tape is first the content of the first tape, the non-empty content of the first tape, then separated by some sharp, so some separation, the content of the next tape, and the content of the third tape. Here the content of the first tape is 100. The second tape is empty, so we'll just denote it with one empty cell, and so is the third. In addition, we somehow need to encode where are the heads of these tapes, and we'll do it by kind of duplicating the number of tape symbols, and for each one of them to have an option that we denote here by a dot of saying, and yes, actually the head is pointing to this symbol. So this is what we have, and somehow, and this is not hard, you need to, as a first thing in your simulation, to turn the input of the multitape into something like this, or to turn, right, and that's not hard because you already get the input on your left, and you need to append it by these empty tapes to the right, and also you need to denote to point that your head is in this position. And then what we do is each time you kind of run through the tape every time to simulate each one of the transitions of the three-tape Turing machine. So let's kind of look at it. It's not hard to implement it in code. So here we moved the head on one. Here we're kind of imagining, just so I don't need to deal with other tapes, that you can also stay put. So let's say you stay put in the other tapes and you implement another move to the right. And whenever you finish implementing one step, you take your head all the way to the left. And now you continue by going to the right, capturing everything that these tapes are observing, all the symbols. You can enter them into your finite state control. And then you know what you need to do, what's the move you need to do, and you implement that. So now in the next point, actually you reached a new cell. So whenever you reach a new cell that you don't have, then you need to go to another procedure that would just make room for this new cell. So you will actually extend the size of this. And in reality, we need to do the same thing for the other two tapes as well. So this is a very high level. This is how you're going to simulate, and actually it's not hard for you to write a pseudocode that does that more formally. So we kind of argued, or I mentioned a couple of times, that some other models are equivalent to Turing machine. We saw a hint how a multitape Turing machine is equivalent. And this leads us to the Church-Turing thesis that says that every model of computation that you will consider reasonable, intuitive notions of computation of an algorithm is equivalent to a Turing machine. Or at least it is captured by a Turing machine. Right, so DFA is not equivalent, but Turing machines can definitely do whatever DFAs can do. So everything that you can do in any reasonable notion of computation, you can do with a Turing machine. Now, this is not a theorem because to formalize it as a theorem, we need to somehow specify what is this, all these intuitive notions of algorithms. Instead, this is, you should think about it as a falsifiable scientific hypothesis. And how would you falsify it? You will come up with a notion, a model of computation. You'll convince the community that it is a reasonable notion of computation. And you'll prove that it can do something that Turing machines cannot do. And this has been tried and failed so far, but it doesn't mean that it couldn't be captured at some point. We will later in the course talk about efficiency, and so I have a stronger variant of the Church-Turing thesis, and this one has been challenged recently more strongly, but so far I'm not aware of any serious challenge to the basic Church-Turing thesis. It doesn't say that it's true, it just says that we don't have any way to counter it. But if we believe the Church-Turing thesis, then much of what we do in this course and whatever we base on this notion of Turing machines is very general. It's not a statement about one model of computation, but it's a statement of every reasonable model of computation. I want to finish this video with two other topics that are somewhat related and also related to what we discussed. One is about non-deterministic Turing machines. So non-deterministic Turing machines will be defined just as in the same way we define non-deterministic finite automata. And it just means that you have multiple possible transitions for a state and a symbol. So instead of having a transition function, you have a collection of possible transitions. I won't define it formally because this will not play a major role in our in this chapter of this course. Non-determinism will play a much more important role in the next chapter of this course. The theorem is that every non-deterministic Turing machine N can be transformed into a Turing machine M that accepts precisely the same strings as N. This is not an instance, I think, of the Church-Turing thesis, because I don't think we can argue that a non-deterministic Turing machine is a model of computation. Or an algorithm, how can you implement this algorithm? It's an algorithm with uncertainty, but it still shows you the power of Turing machines. So I just want to mention that we are only talking here about the strings that N, the non-deterministic Turing machines, accept. What about those that it rejects? Well, it's not completely clear what it rejects or how a non-deterministic Turing machine can reject strings. Because for accepting, we said you accept something if there is some accepting path. But what does it mean to reject? This is not clear. So instead, we are just talking about this notion of recognizing. So M will recognize the same language as N because it's accepting exactly the same strings that N accept. What's the proof idea? There's more details in CIPSR. You just pick a natural ordering of all strings over these over the symbols that can be in the tape, the states that the machine can be, and these sharp. And recall that with these symbols you can create a configuration. This is what needed to specify configuration. So Q and and gamma are needed to specify a configuration. And with this and the sharps, you can specify a sequence of configurations. You can specify a path. And you can enumerate all of these strings. Some of them would lead to a reasonable sequence of configuration, some would not. But every sequence of configuration and every path in N will be specified at some point. So, right, so what you do is pick a natural ordering of all strings, and for every string in this ordering, you check if the string corresponds to a sequence of configurations. And furthermore, this is an accepting computation history for N on W. So every one of these, when you separate the substrings separated by sharp to C0 up to CK, each one of these CIs are a configuration of the machine N. And furthermore, these configurations, so CI yields CI plus 1, C0 is the start configuration on your input on W, and CK is an accept configuration. So if so, you're going to accept, and that's it. Why can't you reject? You can't reject because you're looping over all of these strings. And why does this do what we want? So let me hint about that. And it's just because if W is going to be accepted by M, it means that we have seen an accepting computation in N. So you only accept things that N would accept, right? In a non-deterministic Turing machine, whenever there is a path that is an accepting path, it means that you're accepting this string. On the other hand, if there is an accepting path, if N is going to accept, then at some point in our enumeration of overall strings, we will enumerate this accepting path, and we will get convinced. So M will see an accepting path at some point and would accept W. So that's it about why non-determinism doesn't add to your computational power. And as I mentioned, this is about recognizing. For every N that recognizes some language, there is an M that is recognizing, which is deterministic and recognizes the same language. And the final idea is a different way of looking at computations through logic, or more specifically about the connection between recognizability and decidability through logic. And it will slightly generalize this idea that non-determinism Turing machines can be simulated by deterministic ones. So here is a definition. A definition is that a predicate, which is just kind of a Boolean function taking x and y and outputting true or false, so accepting x or y or rejecting it. A decidable predicate R is a proposition about x and y, the input strings x and y, such that there is some Turing machine M that implements it. So it's decidable in the sense that it can be computed. And it's computed by a Turing machine M that implements it, meaning that for every x and y, R of xy is true if and only if M of xy accepts. So M is going to accept everything where every pair of x and y such that Rxy is true, and it's going to reject every pair of xy such that Rxy is false. And we can think of R as a function from this pair of strings to true false. And let's see some examples. So one example is R of xy is true if xy has at most 100 zeros. So this is one predicate. Another predicate is R of ny is true if so this proposition is that the Turing machine n halts on y in at most 99 steps. So these are propositions. And now we can, with this notion, we can kind of give our theorem that's pretty strong that says that the language A is recognizable if and only if there is a decidable predicate xy such that the language A is can be defined as all the x's such that there exists some y for which R of xy holds. In a sense, y is a witness that x is in the language. So let's prove it. So we want to prove that for every A, it is recognizable if and only if there is a decidable predicate that kind of defines A. Let's start with a case where A is indeed defined this way. And we want to say that A is recognizable. So if A is x such that there exists some y with R of xy being true, then A is recognizable. And the other side that we'll need to show later is that if A is recognizable, then there is some decidable predicate that defines A. For the first one, we're just going to define a Turing machine M that enumerates over all finite length strings y. And if R of xy is true, you're going to accept. And if not, you're continuing the enumeration. So you enumerate all of that. And I want to say that M accepts exactly those x's such that there is some y with R of xy is true. Why this is true? It's true because if there exists some y, then in somewhere in our enumeration, we're going to get to it and we're going to accept. And if there's no y, then whenever we check any y in our enumeration, it's going to fail. And we're just going to run forever. And this is exactly the kind of proof that we use to show that non-deterministic Turing machines can be simulated by deterministic Turing machines. And in fact, if we already had this theorem, we could have used it to prove. It's a kind of a special case of this theorem. So now we turn to the second side, where we want to argue that if A is recognizable, then there is some decidable predicate Rxy such that A can be defined using this predicate. And what is this predicate? You can think for a while. I encourage you to pause me. Well, this predicate actually, we mostly saw it. So let's see it again. So A is recognizable. It means that there is some Turing machine M that recognizes A. And we are going to define the predicate R of xy to be true, if and only if M accepts x in some y, the length of y number of steps. So all y does for us is specify some integer, and Rxy is true if within this number of steps, M is going to accept y. And there are several things we want to do here. First is we want to show that indeed A can be defined using that. Specifically, that if m accepts x, if and only if there exists some y, such that Rxy is true. Why is that correct? Let's see both sides. If m accepts x, then it accepts x within some number of steps. And whenever y is longer than this number of x, then Rxy is going to be true. On the other hand, if there exists some y such that R of xy is true, it means that m accepts x within this number of steps. In particular, it means that m accepts x. The second part is to say that this predicate R is in fact decidable. And in this is it is different than m. And the point is that for m, we cannot really easily decide if m is going to accept x or not. But what we can definitely do is decide if m is going to accept x within some I number of steps. Because for that, all we need to do is simulate the run of m on x for I steps. And then we can eventually, after we simulated, if m accepts, we are going to say it's true. If not, we're going to say it's false. So we don't care if m is going to accept x later on, because the predicate said that m is going to accept x within some number of steps. And that's what makes it decidable. Whereas the language A itself is recognizable because we never know that we can stop. We never know that we don't need to care about the machine M anymore. To formalize what I said, it will be good to have the notion of a universal Turing machine, and we'll have it very soon. The universal Turing machine tells us that you can indeed simulate a Turing machine on some input X. So let's see what we've seen in this video. There are many natural variants of Turing machines, and all the natural variants that we kind of came up with are all equivalent, and we is the entire computer science community. And the Church-Turing thesis says that this is not a coincidence. Now, this is not something that right after we tried so much, we kind of decided that it's probably the case. Actually, the foundations of computer science already come up with this. So Turing came up with this notion of Turing machines, and also assuming that it is kind of universal. So the Church-Turing thesis says that everything that can be computed can be also computed by a Turing machine. And finally, we've seen that non-determinism doesn't add power. And this is unless we take efficiency into account, and we will take efficiency into account, but in the last part of the course. Thank you.